Hi everybody, I'm Gil Kalai from the Hebrew University of Jerusalem and Reichman University. My theory asserts that building scalable quantum computers and even reaching significant milestones towards this goal are fundamentally impossible. Let us move now to a video from 2014 that presents the problem and my approach.
In the 1970s, people thought about what computers could do and what computers could check. They had two ways to go. The first was to believe that computers can do everything that computers can check. This would be great. The second was to believe that computers cannot do everything that computers can check. This would not be so great, but it would be very interesting. And this is what most people believe and try to understand. It would be great to understand it, but even this is very hard. A little later, in the 1980s, people thought about a new kind of computer, the quantum computer, which can do a lot of things that our real computers cannot do. Again, they had two ways to go. The first was to believe that this new kind of computer can be built. This would be great. The second was to believe that this new kind of computer cannot be built. This would not be so great, but again it would be interesting, and it would be great to understand the reasons that it cannot be built. This time, many people took the wrong road and believed that the new kind of computer could be built.
Theoretical physicists, computer scientists and mathematicians developed the theory behind these putative new computers. Experimental physicists and engineers are developing the technology to build these new computers. Quantum computers give many people much hope.
We can build computers that can do computations that no classical computer could do, even if it were the size of the entire universe.
We don't know what the best questions are to ask that computer. That's exactly what we're trying to understand now.
Quantum computers is the wild card. It could be a game changer. It could change the entire landscape of artificial intelligence.
The question if quantum computers are realistic is one of the most fascinating and clear-cut scientific problems of our time. I think that eventually it will turn out that the quantum computation, superior quantum computation and quantum fault tolerance are indeed impossible. Quantum fault tolerance breaks the connection between quantum evolution, geometry and time. So another way to say it is that the failure of quantum fault tolerance is precisely what enables time and geometry to emerge in our physical world.
Kalai's conjectures on how noisy quantum systems really behave can be tested in experiments already planned for the near future, in which attempts will be made to build very stable logical quantum qubits via quantum error correction or by stable exotic quantum gadgets known as anyons.
Repeated failure in these attempts will show that the common beliefs and models for quantum computers and quantum noise need to be corrected. This can be compared to the famous experiment of Michelson and Morley on the speed of light that shattered common beliefs of the time on this matter. Quantum computers may well add to our long list of failures in larger-than-life human quests. Mathematically speaking, Kalai opined, having larger-than-life dreams end so often in disappointment demonstrates how large life itself is.
Does the impossibility of quantum computers means breakdown of quantum mechanics? And again, the short answer is no.
Failure of quantum fault tolerance and quantum computation also gives more room for optimism regarding the ability of our computers to simulate robust physical processes in nature.
Let me briefly describe the situation now in 2025. Over the past decade, my argument against quantum computers have further developed. It is based on two-scale analysis of the models for noisy quantum computers, and it applies computational complexity to argue that there are inherent barriers for the rate of noise for qubits and quantum gates. Over the past decade, billions of dollars have been invested and many experimental attempts have been made. So far, experimental reality is consistent with my prediction that gradual progress in controlling quantum noise will hit a barrier. A few fantastic experimental claims that are in conflict with my theory, like Google's quantum supremacy claim from 2018, turn out to be false, and they represent scientist aspiration rather than scientific reality. Please join us to the Quantum Duel on May 20 in Prague and share the excitement of this wonderful scientific controversy.